Hi everyone, welcome to this episode of Kuipert Labs. In today's video we're going to be discussing separation using chromatography. So I've already introduced you to some of the key concepts to do with chromatography and how it works, and hopefully by now you've also looked at the videos going through some specific examples of gas liquidography and high performance liquid chromatography. But so now we're going to dig just a little deeper to think about how does chromatography actually separate substances, and so how can we use that information to decide how best to use chromatography, what type and how we set it up. So using so we introduced the fact that in chromatography we have two components to it. We have the stationary phase and we have the mobile phase. So the stationary phase being typically a solid or a liquid coating in the case of gas liquid chromatography. So some form of solid or something that remains stationary or fixed during the process. So looking at the mobile phase is some form of a fluid like a gas or a liquid solvent that travel through or over or past the stationary, then facilitates the separation. And then we introduce this idea that in chromatography that the separation is based on two kind of general principles: the attraction to the stationary phase and solubility in the mobile phase. And then we're going to go through each of those in a little bit more detail. Okay, so we're going to have so this first one, looking at attraction to the stationary phase. Now, when we're thinking about both this and then the solubility in the mobile phase, that ultimately one of the key concepts here is polarity. Okay, so I want you to keep that in mind, and the idea that like dissolves, and I might even add to that a little bit. So like dissolves / interacts with like. Okay, because that's going to then give us some underlying information as to how this works. Okay, so let's say that you have a layer of stationary phase. Okay, and then what we've got going up the top here is where our mobile phase is going to kind of pass by. Okay, so it's stuff that's going to make its way across the surface of the stationary phase here. Okay, so if I have, and it's heading this way, just so that you can kind of give an idea. So if I've got a substance, a molecule that's starting over on this side, and then it, and let's say that this stationary phase is polar. Okay, so when we're saying like dissolves or interacts with like, so that polar is going to interact with polar substances, non-polar substances will interact with non-polar substances. Okay, so if I've got a polar stationary phase and I've got a polar molecule, so it's got a little P on it, but there's no way that you can see that. Okay, so let's say that. Okay, this is my polar molecule. Okay, so as this polar molecule that's being carried by the mobile phase makes its way past the stationary phase, there's a strong interaction there. Okay, there's these two things are attracted towards one another, or they interact with, and they kind of connect and make there's intermolecular forces that are going on here. So that then as that makes its way past and keeps getting pushed by the stationary phase, okay, that there's all the way along there are these interactions that occur. And so what that means is that we get so polar solute plus polar stationary phase equals strong interactions. Okay, so when I'm saying the solute, so this is being the thing that's dissolved in our mobile phase or being carried by our mobile phase. Okay, so we get strong interactions, and we would then get a longer retention time. Okay, so the more interactions there are with the stationary phase, the slower it goes. Okay, because it's like perhaps you're thinking of an analogy, right? Say it's like the Queen. in a parade kind of going past, and there's all these sorts of people who are wanting to shake her hand or to give her things. If the Queen interacts with all of these people all the way along, then she travels very slowly. The more interactions that she has, the more slowly that she goes. But if she doesn't interact with anyone at all, or only to a very limited extent, then she can travel faster than someone who's shaking every person's hand. Okay, it's perhaps a bit of an imperfect analogy, but yeah. But so then what would happen then if we had a non-polar solute plus our polar stationary phase? We would get low or limited interactions. Okay, so if we had a non-polar molecule, because it's not interacting with our stationary phase very much at all, it just kind of keeps going straight past. In fact, it would not only is it not interacting with, but it's actually being repelled by the polar stationary phase. So in the same amount of time, that the polar one would be here and a non-polar one would be here, whereas they started off at much the same point back here. So here we get shorter retention time. Okay. Remember that retention time being this idea of how long it takes to pass through the station, or pass by or pass through the stationary phase. Okay, so the more that they are like one another, the stronger that interaction is going to be. The attraction of the stationary phase is also down to, is also down to molecular weight. The bigger the molecule is, the more it's going to be, by inertia, the slower it will travel through as well. Okay, so molecular weight combined with the intermolecular forces at work here means that the stationary phase is a factor in its separation. Okay, let's now have a look at the mobile phase. Okay, so thinking about the solubility in the mobile phase, we come back to our principle of like dissolves like. Okay, and so the more soluble, so the more similar the polarity is, the greater the solubility is, and then we get greater mobility. Okay. Okay, so as far as thinking back to our Queen analogy, okay, that then the more the Queen, or that person, the more they are similar or more likely to be carried by the mobile phase, the more they are going to be traveling along with the stream. Okay, so not only is it about how strongly they pull to the sides or pull to the solid material, but it's how soluble is it actually in the fluid that's moving past. The more soluble it is, the more mobile it will be, and it will travel faster. Okay, whereas when we get different polarity, so polar and non-polar, we get limited solubility, which leads to lower mobility and slower travel. Okay, so this idea being that that when it's different, you get a non-polar substance and a polar solvent, that then it doesn't dissolve in the mobile phase very much. So when it's placed at a certain point, it's more likely to just sit there rather than actually be dissolved in the mobile phase and carried along. Okay, so if we would say, all right, let's look at, like, say, a bit of paper chromatography here. Okay, and so let's look at spots that we would do of 3 different substances. Okay, so we're going to go for a polar solvent, like water or methylated spirits perhaps. Okay, and so we've got the black is polar, blue equals medium polar. It's not really the ideal terminology, but that is, it's not non-polar and it's not polar, whereas our red is non-polar. Okay, we put it in a polar solvent, and what happens is that then the polar solvent is going to make it travel its way up through the bit of paper. What's going to happen, after a certain amount of time, our polar substance is going to be have travelled the furthest. Our medium polar substance will have travelled a small distance, and our non-polar substance has probably barely moved. Okay, you look at then the next kind of time period, and our polar substance has travelled again the furthest. Our medium polar is there, and then let's just say our non-polar one is lagging behind here. Okay, and so when they've started off at the same point initially, that because of the difference in their polarity with one another, and the difference that means they're in their similarity to the solvent, that then they travel at different rates. Okay, and so what we've seen in this video is that there's kind of two. Now I realize that this is a really brief kind of overview, and there's a lot of complexity here, especially because they don't behave independently. That there's all these interactions happening at once. That we can see that the interaction with the stationary phase and the and attraction to it, and the solubility in the mobile phase, both influence the time that it takes for some substances to be separated in chromatography. It influences which ones are going to travel fastest and furthest based on the fundamental principle of like dissolves or interacts with like. Okay, so the more that there are interactions with with the stationary phase, the slower it will go. The more that there are interactions with the mobile phase, the faster it will go. And so we tend to use a balance of these two phenomena to be able to separate out different components. If we can identify which of our samples are polar and non-polar, or perhaps intermediate, then we can choose our materials and our solvents accordingly. Okay, thanks very much for watching. Bye for now.